Here we'll introduce altitudes, which are special lines for triangles. But first, can you identify which pair of lines are perpendicular? Or click down here instead to review. Great, so these two lines are perpendicular, meaning they intersect to form right angles. Now an altitude is a perpendicular line segment between a triangle's vertex or corner and the opposite side. Let's see an example. Here's a triangle, and let's pick a vertex, like this one up here. Let's draw a line segment from this vertex to the opposite side, down here, and we've drawn the line so it's perpendicular to this side. This green line is an altitude for this triangle. It connects a vertex to the opposite side, and it's perpendicular to that side. So next, here's another triangle and a few line segments. Which of these is an altitude for this triangle? Nicely done. So this is an altitude connecting this vertex to the opposite side, and it's perpendicular to this side. Now there are other altitudes here. Which of these blue line segments is another altitude for this triangle? Great, so now we have an altitude for this vertex and an altitude for this vertex. There's one more altitude in this triangle for this third vertex over here. Which of these purple line segments is the third and final altitude? Excellent, so you've identified all three altitudes for this triangle. And notice that all three intersect at the same point over here. This turns out to be true for every triangle, and the point where the three altitudes intersect is known as a triangle's orthocenter. It's a good word to know. Now you can make your own triangle by dragging around these 3 points. We'll keep this side horizontal, and here's the altitude from the opposite vertex to the horizontal side. Notice that right now this altitude is inside the triangle. But it's possible for the altitude to lie completely outside the triangle. Try making a triangle where this dashed altitude is outside of it, and then press the Submit button over here. Nicely done. So here's another example of a triangle whose altitude lies outside the triangle. It's still perpendicular to this opposite side, although it doesn't actually touch the opposite side, but it's still an altitude for this triangle. Now if a triangle has an altitude that lies outside of it, like this one, what kind of triangle must it be? An acute triangle, a right triangle, or an obtuse triangle? If you're not sure, ask for a hint or click here to review these different kinds of triangles. Okay, so just to recap, an altitude is a perpendicular line segment between a triangle's vertex and its opposite side. Altitudes can be inside their triangles, but sometimes they lie outside their triangles, like for this obtuse triangle over here. And every triangle has 3 altitudes, which all intersect at a point called the orthocenter. Here we'll talk about the medians of triangles. Now, a median is a line segment connecting a vertex or corner of a triangle to the midpoint of the opposite side. Let's see an example. Here's a triangle. Now which of these purple points is the midpoint of this side of the triangle over here? If you'd like to review midpoints, click down here instead. Right, this is the midpoint. It's exactly halfway between these two vertices. So the line segment connecting this vertex to this midpoint on the opposite side of the triangle is an example of a median. Next, take a look at these 3 line segments. Which one is another median of the triangle? Right, this is another median. It connects this vertex with the midpoint of the opposite side. Now this triangle has one more median connecting this vertex to the midpoint over here. Now if you look carefully, you can see that all 3 medians appear to intersect at a single point. Is this true for other triangles as well? Let's find out. So with this interactive, you can make any triangle you want by dragging around these 3 yellow vertices. The triangle's 3 medians are shown in light gray. So what do you notice about the medians? Do they always intersect at a single point? So that's pretty interesting. For any triangle, the 3 medians always seem to intersect at a single point. and this point is known as the centroid of the triangle. So next, take a look at this triangle here. Which of these points appears to be the centroid of this triangle? In other words, where do all three medians of this triangle intersect? Excellent. So this point is the centroid of the triangle. And we can see that's right because all three medians pass through this point. Let's quickly take a closer look at this median here. Suppose I were to tell you that this segment between the centroid and the midpoint has a length of 5. Then what would you estimate is the remaining length of the median between the centroid and this vertex on the right? Yeah, so it turns out that this segment has a length of 10, which is exactly twice as long as the segment over here. And the same thing happens if we look at the other medians. If you measured this segment as having a length 3, then sure enough, this segment would be twice as long, 6. And if you found that this segment has length 4, then you'd find this segment has length 8, again twice as long. So in general, the centroid cuts each median into 2 segments, and the longer segment between the centroid and the vertex is exactly twice as long as the segment between the centroid and the midpoint. This is true for all 3 medians. It's a pretty neat fact, and there are a few different ways to prove it, but we'll save that for a later lesson. To start off this lesson, why don't you first identify which of these triangles here is isosceles? Right, this triangle is isosceles. Let's take a closer look. It's isosceles because it has 2 sides with the same length, this side over here and this side over here. Now let's look at the 3 angles in this triangle. Of these angles, which 2 appear to have the same measure? Exactly, the 2 angles down here appear to have the same measure. And notice that these angles are opposite from the equal sides. In fact, this pattern seems to hold for other isosceles triangles as well. In each triangle, we have pairs of equal angles that are opposite from the equal sides. So let's see if we can prove that these 2 angles have the same measure. First, let's draw in one of this triangle's medians. A median is a line segment connecting one of the triangle's vertices, or corners, to the midpoint of the opposite side. So here's the midpoint of the side down here, and let's connect it to the vertex up here. So this purple line segment is a median of our triangle. If you look at these line segments on either side of the median, which of them is longer? Or do they have the same length? Nicely done. The midpoint divides this side into 2 equal segments. So if we were to cut this triangle along its median, we'd have 2 triangles. And notice that these triangles have 3 matching sides. These blue sides that were on either side of the midpoint have the same length. These yellow sides have the same length because we said the original triangle was isosceles, and these 2 purple sides both represent the original triangle's median. As you'll see in a later lesson, whenever 2 triangles have matching side-side-side, or SSS, those 2 triangles will always be congruent. So because these triangles are congruent, that means their corresponding angles must also be congruent. So this angle over here, between this triangle's yellow and blue sides, must have the same measure as this angle over here, between this triangle's yellow and blue sides. So by splitting our isosceles triangle along its median and showing the 2 resulting triangles are congruent, we've proven that these 2 angles opposite from the equal sides must have the same measure. Let's use this fact to solve some sample problems. Here's another triangle, and suppose these 2 sides have the same length, which we can indicate by marking them both with a hash. And let's say you also know that this angle down here measures 70 degrees. Find the measures of the remaining 2 angles in this triangle. Nicely done. Because this triangle is isosceles, this angle here must also equal 70 degrees, leaving 40 degrees for this angle up here. Let's try another example. Here's another triangle, and let's say these 2 sides have the same length. If this angle over here is 110 degrees, then find the measures of the remaining two angles in this triangle. Excellent. Because this angle measures 110 degrees, that means you have 70 degrees left to divide among these two equal angles, so each one is 35 degrees. Let's try one last example. Here's an equilateral triangle, meaning all three of its sides have the same length. Now because these two sides have the same length, that means the angle opposite this side has the same measure as the angle opposite this side. Similarly, because these two sides have the same length, that means the angle opposite this side has the same measure as the angle opposite this side. So in an equilateral triangle, all three angles have the same measure. So in any equilateral triangle, what's the measure of each angle?